All right, greetings everyone. Let's look at number 48 from section 2.5. It says to find a formula for a function that has vertical asymptotes at x equals 1 and x equals 3 and a horizontal asymptote at y equals 1. All right, so got that written down over here. We have a theorem right after the definition of vertical asymptote that you should go take a look at again if you don't remember it. And the theorem says that and it says not in Stewart, by the way, because it was one that's not in our textbook. But essentially, it says when the denominator is 0 and the numerator is not, then whatever caused the denominator to be 0 is going to be a vertical asymptote. So how I can use that here, if I need a vertical asymptote at x equals 1, that means I need x equals 1 to cause division by 0. Uh, 0 in the denominator, but not cause 0 in the numerator. So that means I need a factor of x minus 1 here in the denominator. Similarly, if I need a vertical asymptote at x equals 3, then I need x minus 3 to be a factor of the denominator. Now I can have other factors. It doesn't say, as far as how I read it, only at these locations are the vertical asymptotes, but they're so if I want to put other factors in the denominator, that's fine. What I don't want to do is I don't want to put x minus 1 as a factor in the numerator, because if I do that, then these factors will cancel, and instead of having a vertical asymptote at x equals 1, we'll have a hole at x equals 1. Same thing for x minus 3. What I want to put is, just something up here that's going to fill it out. I can put a constant, I can put x, I can put many things that won't stop this from having those two vertical asymptotes. What about the horizontal asymptote? We need that to be y equals 1. And if I was just to think about this here and ask the question, well, what horizontal asymptote does this graph have in this for this function as is without making any modifications? I would multiply this denominator out. We would get x squared minus 4x plus 3, and then I would see I would have to divide by x squared in the numerator and denominator, divide by the highest power of x from the denominator. When I do that here, this is going to give me a 1. This term will end up going to 0, as will this one. This will also end up going to 0. So this thing would go to 0 over 1. So this graph of f, as it's written now, has a horizontal asymptote of y equals 1. So one thing I can do to change that is just shift it up 1 unit. I can put a plus 1 out here. Now it has a horizontal asymptote of y equals positive 1. And that's perfectly acceptable. Now, if you don't like that or you want to try something else, what we could do is change this right here. I can put a 2 as the exponent on this x. And when I do that, and I divide everything by x squared, in the numerator, that's now going to go to 1. As I said in the denominator, this part's going to go to 1. Those two will still go to 0. I'll end up with 1 over 1, and I'll have a horizontal asymptote of y equals 1. So that's an example. Other examples can also be possible. This is just one that works as well. For 53, I'm just going to comment. I'm not going to write. Okay, so it says to find the limit as x approaches infinity of f of x if, for all x greater than 1, this series of inequalities holds. This should cause you to think of something that we learned back in section 2.3 with the way this is set up. I know it's set up slightly differently than what it was in 2.3, but it should at least bring it to mind. We're taking a limit, or we're trying to find the limit of some function that's trapped between two other functions. That should bring to mind the squeeze theorem. If it didn't, well, hopefully next time you see a similar situation, it will. I know with the squeeze theorem, x was approaching a value, but the squeeze theorem can still be applied in this way as well. So this inequality holds. F of x is still trapped between these two functions. If these two bounding functions have the same limit as x goes to infinity, then f of x is going to have the same limit because it's bounded in between them. So that's what you need to do. You need to go find the limit of this function over here, this 5 root x over root x minus 1. Find the limit of 10 e to the x minus 21 over 2 e to the x. And if you get the same limit, then f of x will have that limit as well. Actually, I'm going to tell you, you're going to get the same limit if you do it right. If you don't get the same limit, you've made a mistake. Go back and figure it out. But that's how you're going to do 53.